Montreal. He is a postdoctoral fellow working on biostatistics with Professor Bouchra Nasri at the University of Montreal. He holds a PhD in statistics from the University of Simon Fraser in British Columbia on high dimensional inference. His research areas include epidemic modeling and analysis using stochastic simulation and missing data methodology. Notre invité aujourd'hui, c'est Dr. William Ruth de l'Université de Montréal. Il est chercheur postdoctoral en biostatistique avec professeur Bouchra Nasri à l'Université de Montréal. Il est titulaire d'un doctorat en statistique de l'Université de Simon Fraser en Colombie-Britannique sur l'inférence de haute dimension. Ces domaines de recherche comprennent la modélisation et l'analyse des épidémies à l'aide de la simulation stochastique et de la méthodologie des données rencontres. His talk today will be on statistical consideration in multi-level mediation analysis. La présentation aujourd'hui portera sur considération statistique dans l'analyse de la médiation multiniveau. Thank you very much for accepting our invitation, and the floor is yours, Dr. Will.
Thank you for the introduction, Idris. So thank you all for being here. I'm William. I'm going to talk about this joint work with Rado, Rowan, Ariel, and Bouchra that I've been doing as part of my postdoc at the University of Montreal. So as soon as I can get my computer to work properly, what I'd like to talk to you about today is broadly referred to as causal mediation analysis. And over the course of trying to implement this analysis on a data set, trying to actually run the analysis and get answers out, we kept encountering barriers. We want to do this, that doesn't work. Okay, well, we'll bring in another set of tools to solve that problem. And now we have another problem that we have to address. So we're going to bring in another set of tools. And that's going to be the structure of the talk today. I'm going to start off by introducing what we're trying to do, the problem we're trying to solve, and then gradually add layers on top of that that allow us to answer the questions that we want to answer. And so the different sections will build on each other, but I'll be sure to bring everything back to the original problem and try to ground it in a concrete analytic context. Okay. So an example where you might use mediation analysis. We're really interested in trying to understand whether or not people will follow restrictive measures in the context of a pandemic. This includes both past adherence, past behavior, and future behavior, trying to predict what they will do in the future based on what they will do in the past. And we imagine that we expect that a driver of this behavior is where people get their news from, and in particular, how trustworthy those news sources are. I'm just going to set my timer here. I know how much time I have left. So we'd like to know if more or less trustworthy news sources will drive higher or lower levels of adherence to, for example, lockdowns or mask mandates. And an feature of mediation analysis, thing that we try to do with this mediation analysis, is to disentangle the influence of news trustworthiness. We expect it to influence both past behavior and future behavior, and we'd like to disentangle the direct influence on future behavior from the indirect influence of future behavior via past behavior. So we've already run into a problem of doing mediation analysis that it gets really wordy really quickly. So I'm going to just go right to a diagram here. We have news source. We expect that to be a direct causal factor for both past compliance and future compliance. And then we expect past compliance to causally influence future compliance. This gives us a direct path where news source can influence future compliance, and also an indirect path that is mediated by the effect of past compliance. So just to set some general terminology here, we call this top path the arc, the direct effect of the news source. We call the center path the indirect effect. And when we combine the two, we call that the total effect of this variable. And it would have been better for me to do these in the opposite order, but we're here now. The exposure in our case is the driving force, the news trustworthiness. The outcome is the variable that we're most interested in understanding. That's future compliance. And the mediator is the variable that sits in the middle and makes the relationship more complicated. And symbolically, we write X, Y, and M respectively for these. And to just anchor this back in our diagram, the exposure sits at the beginning, the outcome sits at the end, and the mediator sits in the middle, with the direct path going directly from X to Y and the indirect path, indirect effect going through the mediator. Okay, so broadly speaking, the goal of mediation analysis is to estimate the total effect and to separate that total effect into the relative sizes, relative contributions of the direct effect and the indirect effect. And historically, the way people have gone about doing this is to fit regression models. So for now, I'm going to talk about this in the context of continuous outcome and continuous mediator, because it just makes the formulas a little bit cleaner. If we write just a utterly classic regression formula, our outcome model is a linear function, or sorry, our outcome variable, we assume is a linear function of the mediator and the exposure plus an error term. And the mediator is a linear function of the exposure plus an error term. Well, with these models in hand, we might define the direct effect of the exposure on the outcome as the coefficient on that variable in the model for the outcome. This is the effect of X holding M constant. So this is a pretty natural way to define the direct effect. And historically, following the so-called Barron and Kenny approach, this is just how we define the direct effect. The indirect effect is slightly more complicated. It's got two pieces here. We take the coefficient on the mediator for predicting the outcome and multiply it by the coefficient of the exposure for predicting the mediator. So we have the effect of exposure on mediator times the effect of mediator on outcome. And this turns out to be a reasonable way to define the indirect effect of the exposure on the outcome. And then finally, we can define the total effect as the sum, direct effect plus indirect effect. So this gives us a fairly straightforward way to separate the two. And it is convenient for us that they add in this way. Okay. So this regression-based approach is quite popular. I mentioned Barron and Kenny. The paper that generally gets cited for this approach has just so many citations on Google Scholar. But newer methods have been developed since. In particular, it's nice to augment this idea of mediation with a causal flavor. To bring in the machinery that's been developed in causal inference world to talk about causal direct effects and causal indirect effects. Causality is a really nice thing to be able to study. So let's take a brief foray into causal inference and then bring that back around to its application to mediation analysis. So the goal of causal inference is to work with the assumption that X causes Y. We have two variables. One is a causal antecedent of the other. And a useful piece of notation or useful definition for articulating these causal relationships is what's called a counterfactual. So we define a counterfactual as the level of some variable Y that we would get if we set its predictor, its antecedent, its cause, to a particular level. So we write Y sub X for the value of Y when X is equal to little x. Okay, this is nice conceptual framework. What would you or would you not follow lockdown measures if you mostly get your news from scientific publications? Would you or would you not follow lockdown measures if you mostly get your news from Facebook? These are two different possible outcomes for a single person that we can at least imagine. and it's helpful to be able to refer to these two outcomes. Unfortunately, in practice, we only get to observe one counterfactual for each person. You actually got your news mostly from journal articles. That's great. And so we can see whether or not you followed lockdown measures. But we don't get to see what you would have done if you mostly just read Facebook. And so if the exposure X is not equal to the value of the counterfactual, then it is really literally a counterfactual. It is counter to fact, and we don't get to see that. So we have to come up with some machinery for what to do about these counterfactuals that are not directly observed. A couple of quick examples just to highlight how this works. If Alice mostly reads scientific publications and follows lockdown mandates, we write y sub science of Alice is follow. And if Alice is just really disciplined, not susceptible to the influences of social media, maybe y sub Facebook of Alice is also follow. Then maybe Alice's friend Bob is not quite so principled, and as long as he reads only journal articles, only peer-reviewed articles, that's great, he'll follow the measures. But as soon as he starts reading clickbait articles, now he's not going to adhere to any restrictions. In practice, we only get to observe what actually happened, but in practice, we only get to observe what actually happened. So we don't actually have a way to distinguish between Alice and Bob. If we only observe the first row, they both look the same. We don't have a way based on data alone to tell what they would have done if they had mostly gotten news from Facebook. Less reliable sources. So what we do instead of trying to infer what a particular individual might have done in some counterfactual scenario, we instead look at population level effects. We look at averages of these counterfactuals over all individuals in some population. And provided that we're willing to make some admittedly fairly strong assumptions, we can identify averages of counterfactuals with averages of populations, conditional expectations from within populations. This allows us to estimate population level differences of counterfactuals using observable quantities. So this gives us a way to estimate, at least at a population level, what is happening with these counterfactuals. And so that gives us sort of some justification for translating our mediation effects into this counterfactual language. As long as there's some hope to estimate effects of counterfactuals, then we might as well use them, because at least conceptually, they're nice objects. It's nice to be able to imagine what would have happened if this person did X. Okay, this is where things get particularly technical. I want to go through these different effects and talk about them, define them. I think they're really good to have seen. The specifics of the definitions are not critical to understand for the rest of the talk. So I'm going to define the total effect of an exposure X on an outcome Y as the expected difference of two counterfactuals. This is the effect on the outcome when we change the exposure from some level X to some other level X prime, averaged across the entire population. That's great. That gets us a starting point, but it doesn't really, we need a little bit more before we're able to talk about direct and indirect effects. And in particular, we need a richer notation of counterfactuals. We need to be able to talk about, well, really, we need to be able to get the mediator involved in our discussion of counterfactual outcomes. So we're going to write y sub x and m. This is, you might call it a compound counterfactual. This is the value of the outcome when the exposure is set to some level x and the mediator is set to some level m. So this allows us to discuss counterfactual outcomes for both the exposure and the mediator. We can also talk about counterfactual effects for the mediator. M sub x is what would happen with the mediator if we set the exposure to a particular level, little x. So this is, would Alice follow lockdown measures if she got her news from peer-reviewed articles and did not follow lockdown measures in the past, for example? And the mediator is, what would Alice have done in the past if she only got her news from Facebook? And this might be different from the same counterfactual evaluated on Bob. With these two new counterfactual definitions in hand, we can actually combine them. So y sub x and m of x, this is what value would the outcome have if the exposure were set to a particular value, and if the mediator is set to what it would have been if the exposure were set to the same thing. So this actually ends up being equal to just y sub x. This is the value of the exposure when the, sorry, oh boy. This is the value of the outcome when the exposure is set to little x, because we set the mediator to be consistent. More interestingly, we can ask what would have happened to the outcome if the exposure were set to a particular value and the mediator were set to some other value. So what would Alice do if she only read scientific articles, but her past behavior is what it would have been if she only read Facebook? So this is now a more complicated effect that we can discuss, and it allows us to ask a richer set of questions, like controlled direct effects and natural direct effects. So the the controlled direct effect, this is, we're going to change the exposure. We're going to start with a particular level of the exposure x, and we're going to flip it to some other value x prime. We're going to do that holding the mediator fixed at some reference value m. So what would Alice do if we're able to increase the trustworthiness of her news sources while holding her past behavior fixed at, let's say, she's always followed everything in the past, we'd like to know what she'll do in the future? This controlled direct effect turns out to be a little bit artificial. We're taking an average across the whole population, but we're going to hold the mediator fixed at some reference value. And this may not be a plausible value for some of the individuals in our population. So if we know that Alice is very diligent about following restrictions, holding her past behavior fixed at not follow restrictions is kind of artificial. Scientifically, this controlled direct effect can be really informative because it allows us to separate the effect of exposure and mediator entirely. But if we want to apply this to a population, we probably want to have some reference to that population for the mediator value. And that motivates this next definition of the natural direct effect. Here, we're still flipping the exposure from x to some other value x prime, but we're going to hold the mediator fixed. I clicked. I need to not click. We're going to hold the mediator fixed not at some reference value, but at what the individual would have done at the reference value of the exposure. So what would the mediator have been if we didn't change the exposure? This grounds the natural direct effect in actual behavior of individuals rather than at some artificially selected mediator value that we just chose. Finally, the natural indirect effect. Here we want to hold the exposure fixed and just change the mediator. And we're going to do that by, well, choosing a level for the exposure. We're going to start with the mediator at that reference value of the exposure, and we're going to say what happens if we change the mediator to what it would have been at a different level of the exposure. Okay, these definitions are pretty crunchy. They take some time to wrap your head around, and I don't want to spend too much time on them. The point that I want to drive home is we can define mediation effects in terms of counterfactuals. And in fact, under assumptions about the behaviors of these variables, we can identify expected counterfactuals with quantities that are estimable from observed data. We don't need to know what Alice would have done if she'd only read Facebook, as long as we have a representative population that obeys certain regularity conditions relating to the dependence, conditional independence between variables. Okay. Well, I think I've already talked about this. I'm going to skip this slide. All right. So a natural question to ask at this point is these counterfactual-based definitions are complicated and take some work. Why did we bother? What does this do to change our analysis? And it turns out that provided all these regularity conditions that I've alluded to are met, our analysis looks very similar. We're still going to fit regression models. We still want to understand, how does this variable, how does the outcome depend on the exposure in the mediator? And statisticians have been studying dependence of one variable on other variables for as long as there have been statisticians. So we're going to fit regression models. We're still trying to predict the outcome using the mediator and the exposure, but now we're going to add an interaction term, a statistical interaction between the mediator and the exposure. And this allows us to deal with, or really it allows us to incorporate these nested counterfactuals into our analysis. The mediator model stays unchanged because there's nothing really to take interactions with in that model. But one thing that the introduction of this interaction term does is now the direct effect, indirect effect, the formulas look very similar, but they now depend on the levels of the exposure being discussed. The direct effect, indirect effect depend on what values of X we're going to plug into our model, because the effect of the mediator depends on the level of the exposure that we're plugging in. All right, so that is causal mediation analysis in a nutshell. We fit regression models, we pull out coefficients, but behind the scenes, there's all this machinery based on counterfactuals, allowing us to interpret our effects in a causal way. All the models I've written down so far have been for a continuous mediator and a continuous outcome. That's because regression models are just easier to write down for continuous responses. But you may find yourself analyzing a data set with a binary mediator or a categorical mediator. And so we'd like to be able to incorporate those variables, be able to handle those sorts of variables in our analysis. And I'll talk about that in just a moment. Another wrinkle that can arise is you might have clustered data. You might have heterogeneous population. For example, in our data set, we have individuals sampled within countries. We've got 11 different countries. And so we might expect that the effect of news source on future compliance may differ across these 11 different countries. And we'd like to incorporate that heterogeneity into our analysis. So the first one's pretty simple. If we've got a binary response in a regression model, we know how to deal with that. We use, instead of least squares regression, we use logistic regression. So now we have a generalized linear model framework, but otherwise the model building is not too much more complicated. You may find it convenient to redefine the mediation effects, not as expected differences of counterfactuals, but as odds ratios of probabilities based on these counterfactuals. That's not the only way to do this. There is another group which does say, yeah, I want to define my effect as an expected difference of counterfactuals, which is a difference of probabilities. But personally, I like comparing probabilities on odds ratio scales. Also, the formulas that you end up using to extract the mediation effects from the regression coefficients look a little bit different, but ultimately you look them up in the literature. These have been derived for us. We don't have to reinvent the wheel. The extension to more than two categories, if you have 3-level outcome, you just do this in the usual way, pick a reference value and use binary indicators for all of the other levels. So this is basically a solved problem. We just extend mediation analysis from continuous variables to categorical variables in the same way we extend any regression from continuous variables to categorical variables. The extension to clustered data, heterogeneous data, is a little bit more complicated. This is based on what's called multi-level modeling or mixed effect modeling. The way we handle this is to add random effects to our model, which I'm going to go into. I'm not going to talk much about the logistic regression extension. I am going to talk about this mixed effects regression because it was mostly new to me when I started working on this project. So I expect there are other people that are also unfamiliar with this methodology. We're going to add what are called random effects to our model, which are going to vary across these clusters. So in my example with the news trustworthiness, the effects of our different variables, the coefficients of our different variables in the regression model are going to vary across country. When we combine this multi-level modeling with the generalized linear modeling from the previous slide, we get what's called generalized linear mixed models, or GLMMs, which are popular, if complicated, shall we say, modeling framework. So that's what we're going to talk about next. The general idea of generalized linear mixed modeling, we're going to augment our set of covariates. We're going to add some variables to our model. We start with an ordinary regression model, and we add a new set of variables. I've written here, I started with y depends on a bunch of x's, and I'm going to add in some z's to our model. The coefficients on the x's are denoted by alpha. These are called fixed effects. The coefficients on the z's, I've written u here. These are not parameters. These are not things that we're going to estimate in a traditional sense. We think of the coefficients on our new variables as, or our new covariates. These coefficients are random variables, which vary across clusters, vary across groups. And so rather than try to estimate these coefficients individually, we want to estimate their covariance matrix, the variance of each coefficient individually, and also the pairwise covariances. Typically, we assume that these coefficients are normally distributed, and so having the variance and the covariance tells us everything we need to know. All right. So the z's are fixed. It's important to note that these new variables that we add in are measured covariates. We don't have to estimate the z's, we observe the z's. The u's are random, and we call them random effects. It's entirely possible that the set of new covariates, z, and the old covariates, x, might overlap. We might have both a fixed effect and a random effect for any particular variable. And in that case, we're going to say we have a mixed effect for that variable. Generally, we're going to treat the u's, the new coefficients, as being mean zero. If the mean's not zero, then we'll just move that non-zero mean over to the fixed effect. And so we don't really lose anything by assuming mean zero random effects. I wrote down linear mixed effect models here. The extension to generalized linear is exactly the same. You still choose a link function. You still choose a response distribution. The only thing that's different is the linear predictor now has some random variables sitting in it. But you handle those random variables, those random coefficients, in the same way, basically the same way you would have if you were working with a linear model. The analysis is just a little more complicated. Why might you want to do this? The first time I ever encountered mixed effect modeling, I was told you should use these models if you have a categorical variable and you weren't able to measure all of its levels. And I think that advice still has a lot of merit. If we were able to measure all the values, all the levels of some categorical predictor, then you just estimate its effects, you take interactions with other variables, and you're done. But if you weren't able to measure anything and you weren't able to measure everything, and you still want to understand the behavior of the levels that you weren't able to measure, then it's helpful to think of the groups that you did include in your data set as a sample of all the possible groups that exist in the population. And that's exactly what this mixed effects modeling does. We estimate the covariance matrix of the random effects of these random coefficients. And a standard analytical question to ask here is, for a particular random coefficient, is its variance 0? And to use the really wordy statistical hypothesis testing language, if we don't have sufficient evidence to say that the variance is non-zero, then we might just drop that variable from the model. If its mean is 0 and its variance is not obviously positive, then we might just call that coefficient 0, and that looks an awful lot like variable selection. Another question you might find yourself wanting to answer in a mixed effect model, and this is the one that drives a lot of our analysis, is maybe you do want to know the specific levels of these random effects within each group, within each country in our case. I said earlier that these aren't parameters, we're not going to estimate them, and that's still true. I've written predict here rather than estimate because these are just random variables that we happen to not be able to observe. So we're going to predict the levels of these unobserved random variables. And there's two standard ways for doing that are either you look within a specific group, within a specific cluster, and you calculate the conditional mean or the conditional mode of the random effect given the observed data within that group. The conditional mode is more tractable to computation, to implementation. I think the conditional mean is more attractive theoretically. So bringing this back to our example, to our data set, we've got people from 11 different countries. We predict the random effects, the random coefficients within each country separately. And we use these country-specific coefficients when we calculate our mediation effects. This gives us now mediation effects which apply specifically to each country individually. We get 11 sets of direct, indirect, and total mediation effects. And then we want to be able to answer questions like, is there a direct effect in Canada? Let's say, is there a direct effect of news source on future compliance? Well, how that really translates to the code that I write is I want to test whether the direct effect is different from 1. 1 corresponds to an odds ratio of 1 means there's no difference between the two levels. And so, I want to test whether these country-specific mediation effects differ from 1. Great. Doing uncertainty quantification for the random effects, for the predicted random effects, turns out to be a challenging problem. So much so that there have been numerous papers in the literature, people just doing empirical studies trying to say how can we estimate variances, standard errors of mediation effects on finite samples, because a lot of the mathematical analysis is asymptotic. And so I'm going to talk next about one way that people go about doing this and one that has worked well for us. And that is the bootstrap. So the motivation for doing the bootstrap is that you've got a really hard analytical calculation. You want to calculate a standard error and you're not sure how to do the math. So you replace this hard math problem with a hard computing problem. And with can I really say with the advent of modern computing, I think in 2024, that's a little bit redundant. With the resources that are available to us, like Digital Research Alliance of Canada is one in particular that I've made a lot of use of. There are computing problems that seem hard initially that end up being very tractable with the power of large-scale parallel computing. So the core idea of the bootstrap, the sort of high-level view of what we're trying to do, we'd like to get the standard error of some statistic. We have a thing that we're calculating on our data, and we want to know what is its variability. And the standard error is defined, if you remember back to an intro stats class, the standard error of a statistic is defined as its standard deviation over the sampling distribution. As I take lots of samples from the population and I calculate my statistic on each of those samples, what is the variance of all the different values that I get? What is the range of values that I get? So if we were able to do repeated sampling from our population, if we could just get more data, classic statisticians lament, if only I had more data, we could just directly estimate the standard error. We calculate our statistic on each of these new samples and call it a day. But in practice, we can't. I can't just say, I wish I had 100 copies of this study. But what we can do is estimate this population distribution. There are lots of tools available for estimating distributions. So we're going to estimate the distribution that gave rise to our original data and sample from this estimated distribution. We can then think of these samples as, well, they're approximately samples from the population distribution. If I sample from an estimate, that's kind of like sampling from the population. And I use these approximate samples to estimate my standard error in the same way that I talked about up here. Generate a bunch of samples. I pretend those are samples from the population, calculate my statistic on each of them, and look at the resulting distribution. That's called the bootstrap distribution. Okay, so that's great as a high-level algorithm skeleton, but there's a lot of decision points we have to make along the way. There are numerous different ways to estimate distributions. I'm going to talk about a couple of them. We do run into the problem of how do I actually do the computing, but this turns out to be a problem which is so-called embarrassingly parallelizable. It's really straightforward to parallelize the bootstrap. And so this sort of becomes a non-issue, particularly if you can run your bootstrap analysis on a compute cluster like DRAC, a problem that would take weeks to months on my machine, I can finish in just a few hours. Once we've done this resampling and calculating our statistic on each of the samples, we then have to come up with a way to translate this bootstrap distribution into uncertainty quantification. And there's a handful of ways to construct confidence intervals based on the bootstrap distribution. I'm going to highlight a few of them and mention a few others that people also use. So 2 different ways to estimate distributions. Again, there are others, but these are probably the 2 most popular. If you've ever heard of the bootstrap, you've probably heard of the non-parametric bootstrap. It's sort of the simplest. Simple is maybe not the right word. It is one way to estimate a distribution. And it requires very little assumptions on the distribution that we're trying to estimate. We've got a bunch of data. We're going to take our total probability and divide it up evenly among the points that we observed. So each observation gets probability 1 over n, and we're going to put 0 probability weight everywhere else, and that is our estimate. It doesn't matter whether the data came from a continuous distribution or a discrete distribution. Our estimate is going to be discrete, and it's just uniform over the observed data. In the next step, when we go to simulate from this estimated distribution, what that looks like is repeated sampling with replacement from the observed data. Resampling with replacement from the observed data is exactly equivalent to simulating from this non-parametric estimate of the population distribution. So that's kind of nice. It's fairly straightforward to implement. Pedagogically, though, I really prefer the second one because I feel like the non-parametric bootstrap hides away a lot of the machinery, a lot of what we're really doing, and reduces it to an algorithm that's really simple to implement, but it lets you not understand what the bootstrap is doing in a way that the parametric estimate really forces you to grapple with. The idea of the parametric bootstrap is to say that you've assumed a parametric model. You did parameter estimates. In our case, we assume a regression model for the dependence of the outcome on the mediator and the exposure, regression model for the dependence of the mediator on the exposure. And so we're going to just choose a member of that parametric family. We're going to take seriously the fact that you've assumed a parametric family, a parametric form for the distribution. We're going to choose a particular representative, which really just means you kind of already did that by estimating parameters. The natural way to choose a member from a parametric family is to do something like maximum likelihood. Once we have this particular representative from the parametric family, we're just going to simulate from that distribution. That gives us a particular estimate. We've chosen it in a way that is hopefully principled. And so now we have an estimate of the population distribution, and we're going to simulate from that. The way we implement that simulation is much more problem specific than the non-parametric bootstrap, and I think that's why non-parametric one is I believe more popular, or at least better known. So let me show what this looks like in our problem. For the non-parametric bootstrap, we look at each country individually, and we resample cases with replacement until we've got the same number of observations in that country as there were in the original data set. So it really only takes one line to say what we do for the non-parametric bootstrap. Excuse me. For the parametric bootstrap, however, we have to be more careful. I've got 6 steps here. So first, we generate random effects. We calculate the linear predictor for the mediator model and simulate the mediator. We use that simulated mediator along with the other variables, the exposure, to get a linear predictor for the outcome, and we simulate that outcome. And at each step, we're using the parameters that we estimated from the original data set. So when we generate the random effects here, the covariance matrix that we're using for that simulation is the maximum likelihood estimate of the covariance matrix, or whatever estimate we happen to be using. It's the estimate that we got from the original data for the covariance matrix of the random effects in the outcome model. So we need those parameter estimates to be able to do the parametric bootstrap. Calculating this linear predictor for the mediator, we need the estimated fixed effects to be able to calculate a linear predictor. And once we've got the mediator, once we've got the outcome, we put this together into a data set, and that tells us, or that gives us the data for a specific country, for Canada. When we then go on to repeat this process for each of the 10 other countries, we get a sample for South Korea and so on. And we combine those back into a single data set, and now we have generated a single bootstrap sample. We repeat this process then some number of times, often hundreds or maybe thousands, depending on the scale of your problem and how much compute time you have. And for each of these simulated samples, we're going to calculate mediation effects, direct effect, an indirect effect, and a total effect. This gives us a distribution of each mediation effect over the bootstrap samples, and in particular, it gives us a distribution for each country. So we have 11 distributions for each of 3 different mediation effects. That's a lot of stuff. What we do with that is it enables us to quantify uncertainty for the true mediation effects based on our original sample. We compare the estimated mediation effects on our observed data with the bootstrap distributions for those mediation effects to say whether our estimates are plausible or not. A way to operationalize this uncertainty quantification is to construct confidence intervals. Once we have confidence intervals, we can use them to also do hypothesis tests. And there are just so many forms of bootstrap confidence intervals. Let's look at just a few of them here. The first one's called the percentile interval. We have this distribution of mediation effects, And to get a 95% interval, we just take the middle 95% of our bootstrap distribution, the 2.5th percentile up through the 97.5th percentile. And that is a confidence interval, it turns out. The second one is a little bit more involved to calculate, but not much, called the basic confidence interval. Here we take our estimate from the original data, we double it, and then we subtract the endpoints of the percentile interval. So interestingly, the percentile interval doesn't use our estimate from the original data. It's not anchored to that estimate in any way. The basic interval is. And just a note, if you ever find yourself having to implement the basic interval, you have to swap the endpoints from the percentile interval because you're subtracting them. So when you subtract the upper endpoint, you get when you subtract the upper endpoint from the percentile interval, you get the lower endpoint for the basic interval, and conversely for the lower endpoints. Finally, the walled interval, this looks like your standard Z or T type confidence interval from elementary statistics. You take your estimate from the original data set plus or minus a multiplier, usually it's going to be 1.96, times whatever the standard deviation is calculated on your bootstrap distribution. So this looks like estimate plus or minus multiplier times standard error, which is comforting. I said I mentioned a few others. There's a studentized interval that looks a little bit more like a T statistic than a Z statistic. There's also a bias-corrected interval, a bias-corrected and accelerated interval. Empirical studies have found that the latter two tend to not perform well in mediation analysis, and so they become less popular in that area. But they are, at least conceptually, theoretically interesting and worth exploring if you find yourself working in a new area. So in general, deciding which of these intervals to use is not an easy problem. They all have different properties, and the best advice I can give is try to find a way to compare them empirically on your particular problem, or try to find someone else that has done an empirical study, a published empirical study in a similar context that you can leverage to help choose which one to use. All right, let's wrap this up now. So putting this all together to complete our analysis, we start off by defining mediation effects, direct, indirect, total, using counterfactuals, using this causal inference framework. We estimate the mediation effects using generalized linear mixed models, and in particular, we get estimates that are country specific. And finally, we do uncertainty quantification for these country-specific mediation effects. We get confidence intervals using bootstrap distributions. All right, just before I wrap up, I've got a few people to thank. The collaborators I've worked with, Rado Rowan, Ariel, and Bushra, all at University of Montreal. And I'd like to thank CANSI, the Canadian Statistical Sciences Institute, for funding my postdoc. And finally, I would like to thank all of you for attending my talk.
Thank you very much.
Hey, that was